Hi, everyone. We are going to be looking at the relative atomic mass, the definition of the relative atomic mass, the definition of isotopes. We're also going to be looking at the list of the uses of isotopes today in this session. So first, I wanted to start off by welcoming you to our revision series, and we'll be looking at our second sets of objectives, which we just listed. Now, the first thing I want you to know is that atoms are very, very small, all right? So they are basically naked to they can't be seen with the naked eye, and they can't be seen with even the most powerful microscopes. So we can't really measure the mass of one atom. However, we actually devised a unit for atoms. When measuring atoms, we use something called the atomic mass unit. So I'm just going to speak about that for a moment here. So the atomic mass unit was designed to describe designed to describe the mass of atoms. Right? So it would be very difficult for us to be talking about the mass of an atom and to be speaking about it in terms of grams. Because if we look at what an atomic mass unit weighs, or what one atom weighs in gram, is almost insignificant. So an atomic mass unit which is a unit that was developed just to be used in chemistry, is actually 1.66 times 10 to the negative 24, 10 to the negative 24 grams. So imagine if we were to keep writing the mass of the atom in grams, we'd have to keep using these big numbers. So instead of having to use these big numbers, we devised our own unit called the atomic mass unit to deal with our atoms, all right? Now, what they did also was that they tried to measure the mass of one specific atom. So they measured the mass of carbon-12. So the mass of an isotope of carbon-12 was measured, right? So that was very tedious for them to do. And it was found to have an atomic mass, or a mass of 12 atomic mass units. Now, therefore, when we speak about one atomic mass unit, we can also say that it is 1/12 the mass of carbon-12, because if one atom of carbon-12 has a mass of 12 atomic mass units, then one atomic mass unit would be 1/12 the mass of carbon-12. So what was done is that the isotope carbon-12 was the one that was measured, and then all other elements were measured in comparison to carbon-12. So we didn't go ahead and measure the mass of every single element on the periodic table. We measured the carbon-12, found the mass of the carbon-12, and then we compared all other elements to it. Now, because all the other elements were measured in comparison to carbon-12, then we put the word relative in front of the atomic mass. So when you are measuring a substance and it is in comparison to something else, well, we use the word relative. All right, so we use the word relative when we are describing the mass. The atomic mass of all elements, all right? So if I say to you, what is the relative atomic mass of magnesium, then I am asking you, what is the mass of magnesium in this unit, atomic mass unit, in comparison to carbon-12. All right. Now, as you can see here, I have some notes about the relative atomic mass. Okay. So the relative atomic mass of an element basically tells you how heavy that element is in terms of atomic mass units. So the relative atomic mass essentially considers all the isotopes that an element has, and then you find the average mass of one atom of that element, right? But you have to consider the fact that it has different isotopes, and different isotopes have different masses. So the relative atomic mass is a mass of an element, all right, while considering its isotopes and their abundances. And this mass is in comparison to carbon-12. All right, so elements have different isotopes. Well, remember we did say before that the identity of an element is really dependent on how many protons you have. So in the case here of magnesium, right, we have different isotopes of magnesium, and they are all magnesium because they all have the same number of protons. So for example, this is magnesium, it has an atomic number of 12, this one has an atomic number of 12, right? So they all belong to the same element, but we notice that the mass numbers are different. So the reason why the mass numbers are different is because they have different numbers of neutrons. So if we should find some magnesium somewhere, if we should analyze all the atoms of magnesium, we will find that 78.99% of the atoms we find are actually the isotope with the mass of 24. 10% of the atoms we find would have a mass of 25, and 11% would have a mass of 26. So all the isotopes, when you add up their abundances, they should add up back to 100%. So it means, therefore, if I said to you, what is the mass of one atom of magnesium? You couldn't just say, okay, all the magnesium atoms have a mass of 24, because that's not true, because there are other isotopes of magnesium. So what we ask, when we ask you for the relative atomic mass, we're asking you to look at all the isotopes that an element has, look at the abundances of the isotopes, and give us an average of that, the mass of the element, right? So when you're calculating the relative atomic mass, you are to multiply each isotope of that element by its abundance. Then you add them together and divide everything by 100. So I have a worked example here for you, and we will do one together. So for example, magnesium here has 3 isotopes. The first isotope has a mass of 24. It has an abundance of 78.99. So we multiply the 24 by the 78.99. Then we have isotope number 2. That is the one that has a mass of 25 with an abundance of 10%. And then isotope number 3 has a mass of 26 and an abundance of 11%. So when we multiply each of the abundances and the masses, we write down the numbers that we get. So this 24 times the 78.99 gives us 1,895.76. 25 times 10 gives us 250. 26 times 11.01 gives us 286.26. Then we make sure that all of that is divided by 100. So when we add up everything in the numerator, we get 2,432.02. Then we divide that by 100, and that gives us a relative atomic mass of magnesium, which works out to be 24.32. So we are saying that if you should take up an atom of magnesium, the average mass is 24.32, and that is after considering all the isotopes of magnesium and their abundances. Now, these values you will actually find on the periodic table. So when you look at a periodic table, so I have one here for you. Let me make it bigger. All right, so if you actually get a periodic table, you will sometimes see that you will have the relative atomic masses listed beneath the element. And now you know how they came up with these numbers. So for example, if we look for magnesium here, we see 12. So the 12 there is referring to the atomic number. So that's telling you how many protons are in the magnesium atom. And this number here is telling you the relative atomic mass. And look at it. It's basically the same thing that we just calculated, 24.31 this would be, just a little bit different from ours. We got 24.32, but how did they come by this number? Well, essentially, they did what we just did. They looked at the isotopes of magnesium, and then they multiplied each isotope's mass by its abundance, and then they added them together and divided it by 100. Okay, so that tells you the relative atomic mass of the element as compared to carbon-12. And of course, when we look at the relative atomic mass of an atom, the units for it is atomic mass unit. So it's not grams. If we're looking at one single atom, then it is atomic mass unit, because one atom doesn't weigh much, all right? But I want you to remember about the relative atomic mass, because it's going to become relevant when we look at the mole concept, because we're going to use the same number here from the periodic table when we're doing our mole concept or mole calculations, because the relative atomic mass is able to tell us the mass of one atom of the element, but it also can tell us the mass of 1 mole of the element. So we'll come back to looking at this in the mole concept. For now, let us see if we could do one here for silicon. Now, if we look at the periodic table, we can look to see what number we should be expecting. So according to this, the relative atomic mass of silicon is 28.08, which is about 28.1, right? So here they are giving us the information. We're going to do the calculations and see if we are going to get that 28.1 as indicated in periodic table. So silicon has 3 isotopes. So the first isotope has a mass of 28 and it has an abundance of 92.23. So we do that first. The second isotope has a mass of 29 and it has an abundance of 4.68. And the third isotope has a mass of 30 and it has an abundance of 3.09. All right, and then that should all be divided by 100. Okay, so let's put that over 100. So then now I normally work out each figure in the brackets, right? So let's do that. So 28 times the 92.23, that gives us 2,582.44. And I'm keeping the decimal places as well. At least 2 decimal places I'll keep. So 4.68 times the 29 gives me 135.72. And then 30 times 3.09 gives me 92.7. And then remember that should all still be divided by 100. Okay. So next I'm going to add all the numbers together in the numerator and then divide by 100. So it's 2,582.44 plus 135.72 plus 92.7. That gives me 2,810.86. Divide that by 100 and then I get 28.1, which is essentially, well, 1. It is very close to what is actually on the periodic table. So they do have 28.08. We have 28.11. That is close enough, right? So now you know how to come and how to calculate the relative atomic mass of each element. So you have to know how many isotopes it contains and what are their abundances. All right, so let us talk more about what isotopes are. So we did say that once you have 2 atoms and they had the same numbers of protons, they were considered to be the same element. But if they have different numbers of neutrons, then they are called isotopes, okay? So isotopes are atoms of the same element that have different number of neutrons. So that means that they have the same, so essentially they have the same number of protons, right? So they have the same number of protons, so they belong to the same element. And they also have the same number of electrons. And that part now is important because if you have the same number of electrons, then this means that you will have the same chemical properties, because it is really the number of electrons that determines how a substance is going to react. Right? And isotopes have the same number of electrons, so they have the same chemical properties. All right? And what do I mean by chemical properties? I mean that they will do the same reactions, all right? So this means that they will participate in the same chemical reactions. So basically we have two isotopes here. We have chlorine 35 and we have chlorine 37. And what I'm saying is that because they have the same number of electrons, they will do the same reaction. So any reaction that chlorine 35 can do, chlorine 37 will do the very same thing. The difference between the atoms though, however, is the mass number. Because, for example, chlorine 35 has 18 protons. And remember, you get the number of protons by subtracting the atomic number from the from the mass number. So that's 18. So if we subtract 17 from 37, we get 20. So you can see that chlorine 37 is a bit heavier than chlorine 35. But chlorine 35 is more abundant than chlorine 37. Now, the difference between the isotopes, though, will be in the physical properties. So it's not in how they behave in the chemical reactions, it's in their physical properties, right? So because one is heavier than the other, the isotopes do have different physical properties. And when I say physical properties, I mean, for example, they will have different densities, they will have different melting points, they will have different boiling points, all right? These are just some examples of physical properties because they have different masses, but as it concerns them reacting in a reaction, they will react the same way. So here you can see the relative atomic mass for chlorine ends up being 35.55 because they did what we did. They multiplied each isotope by the abundance and they divided it by 100. So they added it together and then they divided it by 100. And that is how they came by this number 35.55, which is the average mass of a chlorine atom. Now, let's look at other isotopes. So say, for instance, we have carbon. So most elements do have isotopes. Carbon is another example. We have looked at magnesium thus far. We have seen silicon, we have seen chlorine, and now carbon. So these are just different examples of elements and their isotopes. So carbon has three isotopes, carbon 12, carbon 13, carbon 14. They all have the same numbers of electrons and protons. So they'll all behave the same way in a reaction, but they have different numbers of neutrons. So carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. Now look at the abundance. Carbon 12 is the most abundant isotope here. Carbon 13 is not very abundant, and carbon 14 is not very abundant at all. And I should have mentioned something to you before. When you are actually calculating the relative atomic masses, you will find that the number will come closer to the isotope that is more abundant. For example, look at this example here. Chlorine has two isotopes, chlorine 35 and chlorine 37. When we did our calculation, the relative atomic mass comes out to 35.55. That is closer to this mass number here. So because this was more abundant, then the relative atomic mass will come out closer to that number than the 37, right? So you can actually, before you even do anything, we can see even for the carbon here, the carbon 12 isotope is by far the most abundant, 8.9%. So when you actually see the relative atomic mass of carbon, it's going to be very close to 12 because that's the most abundant isotope. And in fact, let's go back to our periodic table and see what is the relative atomic mass of carbon. It's listed as 12.01 because the carbon 12 isotope is by far the most abundant isotope of the three isotopes that are there. Now, I want to also let you know that isotopes can be stable and they can be radioactive. So isotopes are different forms of the same element. A radioisotope is an unstable isotope of a chemical element that can undergo radioactive decay. Now, isotopes can be stable or unstable. Radioisotopes are the ones which are unstable. Some isotopes show radioactivity, but radioisotopes, all of them show radioactivity. Stable radioisotopes can be found in the elemental form or in combination with other elements in nature, but radioactive isotopes can be found in nature for a short time period. Stable isotopes do not have half-lives, but unstable isotopes have half-lives. And so radioisotopes, which we're going to talk about now, are those unstable isotopes which will disintegrate or their nucleus is unstable and they can emit energy. All right. So the half-life of an isotope is basically how long does it take for it to decay and have its mass decrease by 50%. So that's what we mean by half-life. How long does it take for you to decrease your mass by 50%? And of course, the radioactive isotope has to emit energy. So radioisotopes or radioactive isotopes of an element can be defined as atoms that contain an unstable nucleus, and that nucleus dissipates excess energy by spontaneously emitting radiation in the form of alpha, beta, or gamma rays. All right, so those are the radioisotopes. Now, we have found uses for radioisotopes in various industries. For example, we have industrial applications of radioisotopes, such as, let me look at the common one. We can use, for example, uranium-235, which is used in most nuclear power plants. It's used for naval propulsion systems, for example, to power up submarines, right? So it's used to make nuclear energy, nuclear power plants. It's also used in nuclear weapons, right? So this is mostly an industrial application. We also have sodium-24 that can be used to locate leaks in pipelines in the oil fields. All right, so definitely we can use radioisotopes for industrial applications. We also have a lot of uses of radioisotopes in medicine. So in medicine, we can use cobalt-60 to treat persons who have cancer. That's used in radiation therapy. It's used to prevent or treat cancer. We can use carbon-14 to study the metabolism of patients with diabetes, etc. Iodine-31 to locate brain tumors, monitor cardiac activity, etc., etc. So there are several isotopes that can be used for medical applications. And there's one more use of radioisotopes that I want to talk to you about, which is for research. So the common isotope we use for research is carbon-14. Carbon-14 is used to do carbon dating of organisms and substances. So basically, it helps to tell us the age of fossil or objects that we think are here for a long time. We use radioactivity. Well, we use carbon-14 to determine the age. All right. So we also use it in research when we are researching plants for photosynthesis, and there are other isotopes here. So in questions, they love to ask, what are common uses of radioisotopes? So you would say for carbon dating, to determine the age of objects. It can also be used in medicine to treat cancers or to locate tumors or to study persons with diabetes. And you'll say that in industries, it can be used to power nuclear plants. It can be used to provide energy for submarines, and it can also be used to locate oil leaks, etc., in pipelines. All right, so that is the end of our discussion on the relative atomic mass of elements and on isotopes.